Am I audible? It's good evening, everyone. I hope I'm audible, right? Can you hear me? Shoham tried. Okay, please. So if I'm not audible, please let me know. I've not checked my mic.
You are audible.
Okay. So what I'll do today is I'll finish off. So TD0 we have completed completely. Now is the time to bring in the things that we have learned in the past. That is, we all the while we were learning TD0 algorithm by traversing the Markov chain or the Markov decision process by the target policy pi, right? Till now, our behavior policy in TD0 was the same as the target policy, correct? So that's what we were trying to learn, and we saw that we were able to do it. So we could so we were sampling based on the decision or the based on the policy pi for a particular race. We were sampling the action, and we were learning v pi. That's what we were trying to do. So today what we'll be doing is we will sample action from, as we have done before as well, from a behavior policy beta. Behavior policy. So we did it in session 12 and then try and learn v pi. That is corresponding to policy pi. And we'll quickly see what are the points of convergence and things like that for this algorithm. This is the agenda for today. So everyone do recall, like, right? So what is a behavior policy and what is a policy for what is the target policy? The target policy is the policy. If you look on the left-hand side of the screen, is the policy we wish to learn, and the behavior policy is the policy that we play in the environment. So in any model-free methods. So these are all model-free methods. We don't have access to the model. That is, we don't have access to the transition probabilities. We don't have access to the rewards and so on. All we have access to is data. So the trajectory is generated as far as the behavior policy, where S0, A0, the rewards, S1, A1, we have done this before, right? So we start from S0, you take an action A0, you observe a reward S0, A0, S1, you go to S1, and this continues unless you reach the terminal stage. So this is what we'll be trying to do today, that we will generate this policy, generate this trajectory, generate this trajectory using behavior policy beta. Till now, we used pi itself. Okay, then it's fine. So let's try and recall what the TD0 algorithm looked like. So the TD0 algorithm with linear function approximation said that we wanted to learn the value function v pi as of a state S as phi transpose W, correct? Do you agree? And we learned that the W can be learned iteratively using gradient descent. We'll do a quick recap, but yeah, this is you remember this, right? So this is the big picture that we are trying to remember. So now, therefore, I refer to this temporal difference term as delta n, and therefore this is the form of notation I'll be using throughout today's session to decrease my writing time. So where n plus 1, the W at n plus 1 stage, so you converge until convergence. You continue this. So Wn plus 1 is Wn plus alpha n delta n into phi of Sn, where all the actions were being selected based on the target policy. This is the first thing I wish you to recall, right? So fine. So now I'll come to this off policy method, but let's look at how did this first equation come about. Just to recall, can anyone help me write these steps down? So W star was defined as the argmin, where we were sampling, where D was the diagonal matrix corresponding to d pi, such that d pi transpose p pi was equal to d pi transpose. So this is a stationary distribution. Stationary distribution corresponding to transition probabilities generated by pi. Okay, so clear to everyone? So if it is clear, so can you tell me what was the step to get the update that I wrote down in 1? What was the step that I followed? Quickly.
Yeah, so I differentiated and then I replaced the
Correct.
yeah, then I replaced v pi of s with for a state I would have gotten, if I differentiated I would have gotten v pi of my.
Let us try to differentiate it first. So what is the algorithm that I'm going to use? I'm going to use gradient descent, right? And we have discussed gradient descent in detail. Wt minus alpha t dl dt d omega t. Fine. So let us try to do that for all states. D pi of s, v pi of s minus phi transpose s w squared. This was a loss function. This is the loss function in expanded form.
Yeah.
Just the L2 norm weighted by L2 norm weighted by the stationary probability probs. Fine. So now if I take the derivative, I get, well, there's a half as well. So to cancel out the square, so I'll get s belongs to s, d pi of s, v pi of s minus phi transpose s w square is gone, and phi of s. That's all I get. Fine. So we have done this derivation once again and again, and we have a negative sign as well because of the negative over here. Fine. So once I get this, so
Now
this
I'm
can be
going to use Bellman equation to
yes,
write v pi of s as reward of s dash plus the
very good,
yeah,
very good.
the v pi of s dash, and then we'll approximate v pi of s dash using linear
Correct,
approximation.
correct. So see, look at this equation over here. This equation is an expectation in itself, where so the states are sampled from the stationary distribution, and then this whatever you have in the inside the expectation, this v pi you can just replace by the definition of v pi, that is expected reward summation of I equal to 0 to infinity reward of or gamma times r si ai. So I think I started with t over here, so I'll just put t's everywhere, so s is fine. Okay, this is all right. So si plus 1 given s t is equal to, or s0 is equal to s minus phi transpose s w. This is very simple thing that we had done. And now you take all the expectations together. You can write this as a single expectation, or rather 3 expectations, where source is, so we did this extensively again. Then action was sampled from the policy given the state. And next state is sampled from S comma A, right? This is what we had done. And then in the inside this integral, inside the expectation, this can be written as R of ST or S0 A0 A1 plus gamma times V of A or S1 gamma times V of S1. So this is what we wrote this entire equation to be, and we replace this as R of S0 A0, or just here, since it's S A and S dash, I will just write it in S0 instead of S0 A0s. I'll just replace this as S A S dash plus this. This is from S to S dash via an action A plus gamma times V pi of S dash minus phi transpose S W to phi S. So this is what we had got. And since we have all these expectations over here, we really don't need to do anything. We can just do gradient descent. We can do stochastic gradient descent. We don't need to write down all the expectations. We can just write down whatever is inside the expectation. So we wrote down Wt plus 1 or Wn plus 1 is equal to Wn. And we had replaced, Sutton said that we replace this by the next state, right? And once we do that, I get alpha n, and this entire term becomes delta n, the temporal difference term. Yeah, there's a negative sign as well throughout. Delta n phi or phi of Sn. This is clear to everyone? So what we actually do is we sample from the policy. So we go at a state, we go to a state. State is sampled from first state S0 would be sampled from the stationary distribution, and then from S1 onwards, ST plus 1 is sampled by the policy. Or sorry, rather AT plus 1. AT is sampled by the policy, ST. And once you sample AT, you sample ST plus 1 from the, you observe it is in the data, S comma A, ST comma AT. So this entire thing, ST, AT, ST plus 1 is available in the data. Okay. Now, my question to you is, first of all, what is delta n a function of? So first question is answered here. We wrote it in terms of expectation, and now we'll try to come to the of policy thing. So now first tell me the first thing, what is delta n a function of? Or what is it a random variable of? This is some random variable of Sn, An,
and Sn plus 1.
correct. Given that Wn is known to us. Okay, so this is, remember, we will need this in the future. So remember this. So now I have my update rule given to me. So we come at a state, we see the temporal difference by going to the next state, and then update the weights. Very good. So now once I do that, so here as I had written, here actions were selected based on the policy pi, and also the policy we wish to learn was also the same. So now if you recall in the off policy algorithms that we learned, where the behavior policy, see beta, if you sample the action from a behavior policy beta, what happened was, but the target was pi, we showed something like this happened, right? We showed that if the value function was this, the entire value function as we have defined this, so this is also defined as gt given st is equal to s. We said that we were multiplying a rho t term. It was called a importance weighting term, right?
Yeah.
The importance weighting term, we did it in great detail and we showed that the importance weighting term was nothing but the trajectory, the probability of the trajectory under policy pi divided by the probability under the policy beta. So this is done extensively in session 12. Please go and look. If you have not seen it, please go and see the derivation. So what the big picture goal is, we see the initial expectation was over pi. Yes or no? So initially expectation was over pi and then you had a function in it. Say GT, right? This was your initial, the initial value function you want to learn. Yes or no? Correct? But to do this, we need to act according to the policy pi. Yes or no? Correct?
Yes.
But we don't want to act according to it. Want to act based on pi. So what did we say? We said that since it's an expectation like this, so there could be the probability, the expected value could be the probability of GT under pi into GT. Correct? This was your probability. And we said that we could divide by the trajectory GT under beta. Yeah. So I'll just write in with a different color. We'll get the exact terms a little later, but yeah, the probability under beta and multiply by the GT under beta. So this is all on all trajectories, sum over all trajectories. Okay. So now what happens is we replace this term by a del rho t term, and then see, look at this. This still becomes an expectation, right, over beta. Yes or no? Correct. So this is just lotus again. So the box in green is the function that we are taking an expectation over, and this is the probability density function that we are using to take the expectation. So now you see we can act based on beta. Very good. So this was the big picture idea of the importance weighting and off policy algorithms. Now we'll try to put this off policy algorithm in our TD0 with linear function approximation. First of all, let us try and prove it concretely. See now, what is note that Wn plus 1 is equal to Wn plus alpha n delta n phi of Sn. Okay. So this is, you can note this. You note this down. Now, as soon as you note this, what happens is, now what I do is this function, this update was based on the policy pi. But now what I do a trick. Say that. So therefore, I knew that this term that I had, the expectation term I had over here, let us see what that expectation looks like. So let's look at that. So this term I will write in terms of an expectation first. So let us write it down. So E pi of delta n phi of Sn given Sn. Okay. So now this term that I have over here, that E pi of, so the right hand side over here that I have, how can I write this? So this is for one state, right? This is for, so if you write this delta n down, this is reward of Sn an Sn plus 1 plus phi transpose Sn plus 1 Wn minus phi transpose Sn Wn. Correct? This is the delta n, yes or no? This is a function of Sn, Sn an and Sn plus 1. Do you agree? So now what can I write this? What is this expectation? Can you tell me? What are the terms over which this expectation is being taken? What are the random variables and what is fixed? Yeah, tell me.
Only Sn is fixed and we are taking an expectation over action and Sn plus 1. So
Very
we
good.
sum them over.
Yes, and we will have to take the corresponding densities as well, or the PMFs. Fixed is Sn. It is given. Random variables are Sn plus 1 and An. Right? Now you tell me what is An sampled from in this expectation? Very simple.
Target policy.
The target policy. What is Sn plus 1 sampled from?
Transition matrix.
Transition matrix of the Markov control chain. Or the controlled Markov chain. Okay, Sn. Very good. So now let us write down the expectation. So first of all, Sn is given. So first thing that we want is action based on Sn. Very good. I know this and I know. So if you want me to write it in multiple iterated expectation, that also we can do. This is expected value of where An is selected from. So this is over pi, the policy pi. And then you can write this as, where did it go? Yeah. So delta n phi n Sn under two expectations, right? I can condition on two things, that is Sn and An. Yeah. And I can put another expectation outside over A. Or you can just put the A expectation. So let us try and write it in an easier format. So first of all, we are sampling An. Okay. And then we are sampling Sn plus 1 based on this policy pi. So the distributions here are An based on Sn and Sn plus 1 based on Sn and An. Okay. And now once I write this delta n phi Sn given Sn, I can do two things. So I can already write down the summations or I can represent it in terms of a couple of expectations, right? So I can do that. So first expectation would be over what? When I know, see delta n phi of Sn and An. Do you agree? If I condition also on An, yeah. So this expectation becomes over Sn and An. Do you agree? This transition matrix, because now we have conditioned based on these joint distribution. Now I just can't condition, right? So once I get this distribution, what should I next do? I should take an expectation with respect to, tell me. An.
Yes, the policy.
The An based on the policy Sn. So basically what you'll do is you will condition again on Sn, right?
Can I be heard?
Yeah, you can hear. I can hear you. Go ahead.
No, it's all right. I was having an issue.
Yeah. No problem. So basically what you're doing is first, this is the conditioning on Sn. And then since you do not know An, I again do an iterative conditioning. That's all I have done. So that's the expectation that we'll get. So let us try and write it down. So what will this become? This will become summation of pi of A given S, because where is this, or rather Sn, can write An in action space of Sn into summation of Sn plus 1 given Sn An into delta n phi of Sn. Yes or no? So this is the inner summation and this is the outer summation. Sn plus 1 in S. Clear, everyone? So now what can I do? I can play a trick again. I can multiply and divide something like this. I can multiply by beta of An given Sn and divide by beta of An by Sn. I can do that, where beta is the behavior policy. Do you agree?
Yeah.
So once I do that, look at this.
That becomes the row term.
Correct. So now I can write this as the summation over An, beta of An given Sn, summation of Sn plus 1 in S. This is rho n into delta n pi of Sn, pi of Sn plus 1, Sn comma An. Very good. Now you see it's the same expectation again. So I can write this as expectation over the policy beta and rho n delta n phi of Sn, given Sn is equal to S. Now just Sn, since I've written Sn. Clear? So this is what I proved. Okay. Fine with everybody? Clear? So now what I do is, you see, they have an expectation in terms of rho n and so on. I had Wn plus 1 as Wn plus alpha n rho n phi n when I selected based on, when the expectation was based on pi for rho n delta n given Sn. So now, or not rho n, sorry, phi n Sn. So now I want to sample based on beta. So what will I do? A naive approach, we'll see if it works or not, is to naive TD0 of policy, naive of policy, see TD0 algorithm. You can write this as Wn plus alpha n. What will I do? This is, look at this expectation now. If we are sampling from expected value of beta pi of Sn delta n rho n Sn. I'll just replace this what?
Inner term. In that inner
Correct.
term.
Rho n delta n and phi of Sn. That's all I'll do. So this is your naive TD0 with linear function approximation. For this is also for off policy. Can be written as this term, or Wn plus 1 equal to Wn plus alpha n pi of A given S by beta of A given S, and you have delta n phi of Sn, where An is sampled from behavior policy at every state. Clear to everyone? Any questions?
Yeah, could you just sum up the proof in like in 10 seconds? What
Correct.
you, yeah.
All I did was I wrote down the expectation on the right hand side of this equation. Okay. Which was
Okay.
based on the target policy. On target. And once I wrote it on the target policy, I saw that I just want an expectation in terms of Sn. So therefore, I saw what are the random variables that Antariksh helped me to find out. The random variables were An and Sn plus 1. So I wrote down the corresponding expectations. Fine.
Fine.
So once I wrote down the corresponding expectations, I multiplied and divided by beta and then replaced rho n as pi of Sn An given Sn by beta of An into Sn, right? And then the expectation turned out to be over the policy beta.
Using
That's
local.
it. Yeah. So as soon as we do that, we can say that we just replace the initial term that we had with, we just multiply the importance weighting term, importance ratio. Importance weighting ratio. Very good. We have derived this as well. Now the last part of this is to see. So what we now know the algorithm, all right, but we do not know will this algorithm converge to the same point as we want it to converge, right? Do you remember the point of convergence of the previous the point of convergence that we derived for the TD0 with linear function approximation for the on policy case? We derived a bunch of equations and we tracked the ODE and we found out a very, very nice solution. The W star was A inverse B, yes or no? And we said that this was a globally asymptotically stable equilibrium. And this was unique as well, right? We showed that it was unique by showing that this function was invertible. This matrix was invertible, right?
Yeah.
So this was the big picture story. So now we will have to see if this algorithm. So we'll quickly do whatever we did again, but we already know stuff from past. So this will take only a couple of minutes to write down what are the martingale sequence, what are the update equation. So let us write it down. So tell me first, the first question is, I know the update, right? I know the update as alpha n rho n delta n phi of Sn. So now first step, what is the first step? Yeah,
Make it
to write
stochastic differential equation by
very
taking
good.
into the left side.
Very good. We have to make it into an SDE of a specific format, right? So first we will assume a history, which is the collection of S0, A0, same. It's nothing is going to change. S0, A0, W1, S1, A1, all the way to ST or SN in our case, right? Just writing N always. And AN is just not used. Okay, up to SN is being used. So now, first step is to introduce the martingale, right? How do we introduce the martingale? This function is a function of, so
plus minus expectation, right? Yeah.
yes, expectation. There's a specific for this sequence. There's a specific thing for the expectation. So this is just not an expectation. We'll have to take an expectation with something given to us, right? This is what we given the entire history, correct? That's what we said. So now this is again only depends on people we have done this before. Rho n delta n phi Sn. What does it only depend on?
We are going to sum out the Sn plus 1 and An, so it only depends on Sn.
No, what is being given? Correct, that is right. It only depends on Sn and This is given to us.
Sn and an.
Yeah. An is not given, no? For the history given to us, it's given Wn and Sn is given.
It only depends on Wn and Sn.
Correct. So the next term only depends on Wn and Sn. Very good. Great. So now this expectation is being computed over which policy? Which policy do we want it to be computed over? The beta n policy, right? Because that's how we are selecting the actions, right? No questions? So as soon as I get this, can you tell me what can I use? I have already derived one equation. I can change this instantly. I can do this instantly. Can you tell me fast? Just now we derived it.
Yeah, it's equal to e pi delta n.
Correct. Very good. See, we just now derived this equation. Where did it go?
Yes.
The equation, say this, we call this equation 1. So by equation 1, that is the temporal, this is the importance weighting change in expectation based change in expectation. Very good. So now as soon as I have this is exactly the term f of WTST, yes or no? This is what we had derived in off policy. Yes. Very good. So now you see, I already know this from our, so I'm just told to find WNSN. So I can easily do that. I remember that as well. It is R of Sn plus, what was it? Summation of pi of S to S dash over all S dash in S over the policy pi transpose S dash W n from Sn, of course, minus phi of phi transpose S n W into phi of Sn. This is exactly what we had got. Yes or
Yes.
no?
Yes.
Very good. I think this is correct. It is. So now this is not important. Today's session is not about finding this because we've already found out the results. So this is just for you to recall the equation. So the martingale becomes Mn plus 1 becomes, tell me, rho n delta n pi of Sn minus
The expectation over pi of delta n phi
Capital
of f of capital F of W and S.
correct. That's what your martingale becomes. So now I can write the stochastic differential equation as Wn plus 1. So I will write this, martingale, I'll just represent this as naive TD0. Okay, so because there'll be a lot of martingales coming up now, plus alpha n. I can write this, this is the same WNSN plus the martingale n plus 1, naive TD0. Very good. So now whenever we have this sequence, we said that it tracks which ODE? Summation of f of, yes or no? And we had something else here. Which ODE does it track? Session 15. How did we find out the closed form solution? What did we multiply this with? D of S, yes or no? The stationary distribution. I'll just show where it is. See? So for any Markov chain induced by YT, if nu of y is the stationary distribution, then any martingale equation in form of the SDE can be written to be tracking this ordinary differential equation. Yes or no? Where we have this entire f of omega tst, whatever we have, wtst, multiplied by the probability of the stationary distribution, correct?
Yeah.
So that's all. So now you tell me, what is Sn to Sn plus 1 being obtained from? By the action An? Yes or no? Correct?
Yes.
So therefore, the stationary distribution, the Markov chain is corresponding to which stationary distribution? The which probabilities? Corresponding is corresponding to which policies?
Beta.
Yes. So therefore, it is corresponding to the P of beta. Yes or no?
Yes.
Because we have been selecting these actions based on the every state, whatever ODE we are generating. Recall that the f of omega n or wn sn is, this is being multiplied by the stationary distribution ds, the stationary distribution of the Markov chain generating states sn plus 1 and so on. Yes or no? Correct?
Yes.
So this will become d beta. So now everything is the same, only one thing has changed. What is that? Initially this is for naive TD0 with linear of policy again. Function approximation. So, but what was the original one? This was d pi of s. Yes or no? Correct? This is for TD0 on policy. Correct? Now, for this, what did we get? W star to be? W star to be? Do you remember?
W
We
star
got?
it as A inverse B, where otherwise we can write it as phi transpose D into I minus P pi in P pi
Yes.
gamma P pi into phi
Okay.
within the bracket only.
Yes.
Then phi transpose D, yeah, inverse phi transpose D into R.
Good. This was a reward.
Yes.
And this is d pi. What was d over here? This is for on policy. This is for on policy. So this was diagonal of d pi of s, right? Stationary distribution of policy pi based on policy pi or target. So now tell me what will just change just by comparison. So therefore,
The D matrices would change and also P pi.
E won't change because
Yeah,
F is still
because
the same. F is still the same, right?
yeah, P
No,
is essentially the transition matrix from S to S dash.
correct.
So it's going to be the same, but could I clarify one thing? The in the stationary distribution you have written in the left that P beta is basically P given S and A, right? Right.
P given, so this is P from S to S dash, S to S dash under policy beta.
But the matrix would be the same, right? P S dash given S.
So the transition matrix would change, right? So transition, see, there are two distributions, yes or no? There is given state and action, correct? There is a probability, correct?
Yes.
So transition, so this is your normal matrix that is given, that is fixed, correct?
Yes.
But what is P of S dash given S?
That's
This is,
the policy multiplied by the P give S given S
so let
dash and
us,
A. So
so
I get it now.
S dash into beta of A given S, correct? Summation over all actions, correct? So this is B beta. P pi would be, because it depends on the policy. Yes or no? This is how it's different.
Yeah, got it. Got it. So only the d pi should change to d beta.
Yes. So comparing 1 and 2, the off policy equation is W star. So I will write it in this form. D beta 1 minus gamma p pi phi W star is equal to pi transpose TR. Okay, clear? So now everything remains the same except the d beta is the diagonal of d beta of S. That is the what is it, that the stationary distribution corresponding to policy beta. Very good. So now we have seen the point of convergence. All right. Thus, is it the no? It is not the same fixed point. Moreover, is this guaranteed to converge? Show that it is not guaranteed to converge to a unique point. So all we need to see, till now we were showing that this was unique, because why it was unique? Because this was invertible. Yes or no? Do you agree? If invertible, then W star of policy is unique. This is off. So let us see that it may not be unique. Why is it not going to be unique? So let us write. So what did we do to show that it is invertible? We said that we used which property? A positive definite matrix property, right?
Yeah.
Positive definite matrix, that is Z transpose AZ. So I will represent, say this as A dash. A dash question mark, is it greater than 0 for off policy? Let us see if it is greater than 0 or not. So again, we did it like last time. Z transpose phi transpose D beta. So Z transpose A dash Z is equal to this. Phi of Z minus, if you're not following, please stop me. You know the D matrix, the A matrix. This is the A matrix. I'm just multiplying Z and Z on both sides, writing the quadratic form. This is phi transpose D beta P pi. Do you see the difference that we had from last time to this time? What is the only difference here? The only difference is this product. This was d pi into p pi. But now we have d beta into p pi. Look at this. What is this? I can write this as y transpose. Say I write y is equal to phi z. I can write this as y transpose d beta,
which is the d norm.
which is the d norm, minus y transpose d beta p pi d into y. Very good. So this is the d norm squared minus, I can do something again. I can write this as y transpose d beta. We have done this before. Half p pi of y. And this term, let us look at the second term, term 2, as we did last time. It's y transpose d beta to the power half d beta to the power half p pi y. What can I use? I used it like last time. This is a vector. This is a vector. What can I do?
Cauchy-Schwarz inequality.
Cauchy-Schwarz inequality I can use. So I can use Cauchy-Schwarz and I can write dt to the power half y and db to the power of half p pi y. We showed that this was equal to the, again, recall, Z transpose or y transpose dy can be written as,
Yeah, it can. We showed that it was equal to the length of. It was y d norm of y to the only d norm
just
of
d
y.
norm, correct, the d norm of y. I'll just write it down here since it's a very easy proof to do. So d to the power half transpose d to the power half y. And this is basically writing it to be d to the power half y square root. This is equal to d to the power half y. Okay, so this is what we had shown last time. So this is clearly I can write d beta to the power y, and similarly I can write this as p pi y, again d beta. Fine, very nice. So now this term, second term, we had written it down in terms of, remember, p pi y d beta squared could be written as d beta of s, s in s, and the inner summation, yes or no? S dash in s, pss dash under policy pi y of s dash squared. So I did this last time, session 16. So I'm going fast. So what will this become? So what did I use then? This was expected value of
Yeah,
ys square.
yeah. Then I showed
Ys,
the inequality that it's uh, less than equal to ys squared. Uh, yeah, we used Jensen's input.
Jensen's inequality, the expected value. So I could write it as in terms of d beta s summation of p s to s dash to pi y s dash. So please go back and look at session 16. This has been done in great detail. So okay, this is fine. So once I do this, yeah. Now
No,
you see there's a problem. Ys dash squared. I reordered the summations. And I have a big problem over here. D beta of s. So now, do you recall what did I do next after this? I said that this term was again equal to, if this was d pi,
it would
if
have been equal to d pi because it was stationary.
it was stationary. Very good. If d pi, this is equal to d pi, but d beta p pi is not equal to d beta. Therefore, this entire term will become another distribution. So let us represent it as d beta tilde. So this will become d beta tilde s dash summation of s dash in s y of s dash squared. So this becomes, what does this become? D beta delta y squared. Yes or no? So this becomes p pi of y is equal to d beta tilde. Okay? Which is not equal to y of d beta. So as soon as this happens, this entire term, I can write this down as, I know that this is upper bounded by d beta and y of d beta delta bar. There's a gamma as well. I forgot. You did not remind me either. Okay, now this term, last time this was same as d beta. Yes or no? This was equal to. So now let us look at this term of the on policy, off policy case. Z transpose A Z can be written as, or written that greater than equal to y d beta squared minus gamma times y times d beta into y times d beta tilde. Yes or no? Which can be written as yes or no? I can write this.
Yes.
And this term can be less than 0 if y d beta delta is less than y d beta. Gamma times, of course. So therefore, inverse is not guaranteed to exist. So now I have a, now you can, if you have any questions, please ask me, and we'll see the last improvement by Sutton to solve this problem, which is called the emphatic TD0 algorithm. I'll just introduce the algorithm and we'll stop there. We'll not analyze it very, very deeply. I have given reference to the paper as well. If you are interested, please go and look at it. Yeah. Is this clear to everyone? Any questions? Especially regarding, yeah.
Yeah, got it.
Great. So let us look at what the interesting part to it is. So we said that W star of policy is not guaranteed to have an unique fixed point. Okay, so let us now see what did Sutton in 2017, very recent paper by Reinforcement Learning Standards, which has been learning for centuries now. So it says that there's a solution to solve this problem. So let us look at the solution first and try to analyze what this solution is actually trying to do. We'll do exactly the same thing that we did now, but I'll, for the interest of time, not write down the entire algebra for the point of convergence and so on. We'll get to the point of convergence directly by using comparisons. Okay. So do you agree this was the off policy update was Wn plus 1 Wn alpha n delta n rho n pi of Sn. Correct? This was your off policy update. Now, what Sutton says is when rho n is equal to pi of n Sn by. He says that, okay, since this is not converging, I add another term to it, the Kn term or the emphatic term. This is also called the follow-on trace because it keeps track of the entire history. Keeps track of entire history and helps in convergence to a unique point. Okay, so now how did he define this Kn term to be? He said that Kn is equal to gamma times rho n minus 1 Kn minus 1. So it's a recursive definition plus 1. This is one of the choices. There can be multiple choices and this would still hold, but we will select this choice and see if it works or not. Okay, is the definition clear? So let us try and write down a general form of Kn first. Question 1 is write a general form for Kn. So what is Kn? Again, rho n minus 1, Kn minus 1 plus 1. What can I write Kn minus 1 to be? Help me.
Gamma rho n minus 1 k minus 2 plus 1.
2, both will be 2, right?
Yeah.
Yeah, sorry.
Correct. So this becomes gamma square rho n minus 2 minus 1 Kn minus 2. I will write one more term. It will help you.
So we could go to the K0, right? Like this.
Correct. Exactly. That's what I'll do. So gamma square rho n minus 2 rho n minus 1 gamma times rho n minus 3 Kn minus 3 plus 1 plus gamma rho n minus 1 plus 1. This becomes gamma cube rho n minus 2 rho n minus 1. Sorry, rho n minus 3 rho n minus 2 rho n minus 1 Kn minus 3 plus gamma square rho n minus 2 rho n minus 1 plus rho n minus 1 plus 1. Is this fine? Clear? So now, by induction, what will the first term be? How can I write this? A pi of I equal to 0 to, see, how much will it go to? See, you have 3 now. Corresponding to 3, you have a gamma cube, right? So if you have all the way to 0, so what will you have? Gamma to the power?
N. We'll have gamma to the power n. If we go K0, right?
You will have gamma to the power n. That is right. So let us try and write that one moment. This will be, so you have a term all the way to 1. And then what else do you have? You have, let me just look at this once. The first term, so there will be one term. Let me just look at it. Is this correct? Yeah, this is correct. So this is 1, this is gamma square, gamma cube Okay, there is a kn minus 3 term, right? So this goes all the way to k0, right? So you will get, when it goes to k0, what will you get? K0,
we'll get product of pi of I equal to 0 to, gamma to the power n, pi of I equal to 0 to n, rho of n minus I.
0 to, so this
Or
is
simply,
k0, yes, n minus 1, up to n minus 1 we are multiplying, 3, 2, 1, 3 terms, and we have n terms over here, yes or no?
yes.
From 0,
Yes. 0 to n minus 1, rho of I.
rho of I. This is the first term that I'll get. So there's a small mistake in my notes. That's why it was got confused. Yeah. And then what else will we have? We will
Then,
have all
yeah,
these terms.
Yeah.
So let us write this down. What is this terms? What these terms can we write this down as? We can write this down as. See, there are two things over here. Let us note this. See there, see gamma is 2, you have two terms of rho. Gamma is to the power 1 term of rho, and so on. So what does it mean? It means that for every I there is a, so if it is 2, it will have 2 terms, correct? If it is 3, it will have 3 terms. It will have 4, it will be 4 terms, yes or no? So if we write a summation,
Gamma to the power I pi of rho n minus 1 from I 1 to n minus 1, I think.
yes, summation can be from 0 because I have 1 here, correct? Gamma to the power 0 has to be also there,
yes.
all the way to n minus
1.
how many term? N minus 1. Because see, is it n minus 1 for 3 as well? Yeah, for 3 you have up from 2. Very good. So now I could write this, or I could write it in the reverse order, whichever way is easier for us. So it is C into pi of the product from j equal to, say, I plus 1 to
N minus
n
1.
correct. So I plus 1 to n minus 1. If I write this, I can write gamma as n minus I minus 1, right? And then I can easily write rho of j. Is this correct? See, if I put I equal to 0, so I don't want to put this in the subscript, so it becomes easier in this way. So rho equal to I equal to 0 means gamma to the power n minus 1, right? And this term starts from 1 all the way to n minus 1. See, you will get 1 rho 2 dot 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 rho n minus 1. That's what we want. We want n minus 1 terms, correct? A easy case to understand this is I equal to n minus 1. If we take I equal to n minus 1,
Dada,
this,
I think
yeah,
it would be simpler to write the first summation as I plus 1 on, I
you can
mean
write,
as j, like j, and then it would be j equal to 1 to n minus 1, then it would be r n minus j,
see,
product of,
this will just be different. This will be j minus I. So first summation, you'll write rho to the power I, right?
yeah,
Okay.
it's okay. What I'm saying is that you wrote it as n minus I plus 1. So I suggested that you could write the left
Okay.
summation as also j. Then you could
Yeah.
write it as j equal to 1 to, I mean,
Okay, you say this summation, k
no, no,
term.
no, no, no.
Then
I was saying that you could write the summation as summation j equal to 1 to n minus 1, gamma to the
oh,
power
I
n
wrote I.
plus,
So
yeah,
I wrote, so one is I equal to 0 to n minus 1.
yeah, okay. And then you wrote the product j equal to I plus 1, and then you change the gamma equal to gamma to the power n minus I minus 1 to
Yeah,
make the
this,
equation correct.
yeah, I did that. So I'm asking, what should I do?
No, I just
First,
suggested that
yeah, tell
uh,
me. See, the first term can be gamma to the power I. I can agree to that. See, for the first 0th term, correct? This, and we will not have any other terms, right?
Yes.
That is okay. So now, so then the j has to be changed, right? It should be between n minus I minus 1.
Yeah, that's what would be changed if we write it as this.
Correct. So if you write it as this, it will be j from j equal to n minus I minus 1 because we have I terms, right? At the end of the day. You are telling this, you want to write this. This is also fine, no problem.
I was actually saying that we could have written it as summation j equal to 1 to n minus 1 gamma to the power n minus j.
Okay.
J equal to 1 to n minus 1.
Okay.
In the left also, left one also, we could have written j equal to.
The left equal also. I know, but there's a k0 term there. The k0 term is the point of conflict. Otherwise, I could have written a single term. That's what you're suggesting, right?
Yeah, I was just suggesting that we could write summation j equal to 0 n minus 1. Not j equal to 0. It would start from j equal to 1, then it would be gamma to the power n minus 1, then and then onwards. That's what I was suggesting. Yeah, n minus j. If now product j equal to now product is from j to n minus 1. That's what I was saying. I
Okay,
equal
this
to
is
j to n minus 1 row of I. That's what I was saying. Nothing more.
this. Yeah, I understood this term. So 1, 2. Okay, but this does not take care of rho to the power 0, does it?
No, it doesn't take care of rho to the power 0.
That also has to be taken
That's
care
fine.
of. Yeah, so that's why I was thinking of this. So you could write I rho to the power gamma to the power I, doesn't really matter. So gamma to the power I is the first term at 0. I want my summation to range from. If you do not want to put indices there, we can put it in the sum as well. J equal to, from where to where will I sum? Will I multiply? J minus I. Yes or no? Is this correct? Yes, this is correct, right? This is fine. See, when I equal to 0, I will have the inner summation, the inner product running from.
Yeah, this is fine. This is fine.
This will run from n to n minus 1, which will become 1. I equal to 1. This is 1. This will be gamma. The summation will run from n equal to n minus 1 to n minus 1. This will become pi of n minus 1 and so on. It is correct. So this also you can write. Okay. If you like this is better. Fine. So this is now I will write kn rho n and I'll show you that this term is even looks better. Rho n pi of I equal to 0 to n. Right? I multiplied rho n. So if when I multiply rho n with this, kn rho n. So rho n, if I multiply, right? So this term will become, just tell me, just the nth terms will come up, right? I equal to 0 to n minus 1, gamma to the power I, j equal to n minus I to n rho g. Correct? This is what I'll get. Yes or no?
Yeah.
The last term I'm just multiplying. Okay. So now this is done, the general form. So now I'm asking you, is this kn? So first thing is, if you are taking an expectation, what does it have to be? It has to be bounded, yes or no? The kn, look at this, the summation that you have over here. Look at this term. That this entire term that you're getting, do you see kns are getting accumulated? So as n tends to infinity, So number 2, as n tends to infinity, so these terms will become larger, right? More terms will be there. Yes or no? Because of kn? Questions? As n becomes very high, in wn plus 1 equal to wn plus alpha n, kn, rho delta n, rho n, phi n. Okay. As n goes high, kn is going to increase. The number of terms in kn will increase, yes or no? Clearly, I can see this in the summation. So now I have to say that, is this bounded or not? Does it asymptote? Let's see that. So let's kn. I take the mod. Kn is again upper bounded by mod of kn, which can be written as, can you tell me? What can I write this as by triangle inequality? Gamma to the power n I equal to 0 to n minus 1. So I'm just using this equation over here. Rho I k0. Okay. Plus, look at this equation over here. What will this become? Tell me. Plus the summation of, are you following? What's
Yeah.
the second term?
Summation of
Okay, summation of,
I from 0 to n minus.
okay,
Mod of that into mod of
this. Is this good? This is going to be that. Correct?
Yeah.
So now see, I will say rho I is, what is it? Mu I by Si by beta I, or sorry, pi I by Si and beta I by given Si. Yes or no?
Yeah.
Correct?
Right.
So I'll say that this is bounded by some C. Let this be bounded, that is, there does not exist a state such that beta of ai given si is equal to 0. That is, for all a, beta of ai given si is greater than 0. This I can assume safely, because anyways division by 0 is not possible, right?
Yeah.
So then if that is true, I can bound it by capital C. This is between 0 and C. So as soon as I do that, what can I do? I can write this as, see, for all I it is bounded to the power n.
So I can write it as c to the power n minus 1.
So to the power n, there are n terms.
Yeah, sorry. The 0 to n minus 1. So n.
Yes. Plus 1 plus gamma c plus gamma c square plus gamma cube c cube and so on. Yes or no?
Yes.
See, there are how many? There are how many terms over here? I terms. Is it correct? See, I, if there are 0 terms, 1 term, 2 term.
Yeah.
Yeah,
Items.
there, I terms. Correct. There are I terms, so I will have a summation over gamma to the power I, c to the power I. Yes or no?
Yes.
C to the power I, c to the power I. This is upper bounded by c to the power I. So this will become, so if I say max of k0 comma 1 and I say that this is some k tilde, then I can further upper bound this by k tilde 1 plus gamma to the power. This is what Antariksh was telling me. Write a single summation. Yes or no? Do you agree? If gamma c between 0 and 1.
Yes. And then that can be represented as a like a GP sum of.
You don't even need to do that. It is, you don't even need that. So k tilde, this GP is, the sum of this GP is 1 by
1 minus R.
So see, yeah.
But
So
n is, we need to consider n. So alpha n
yeah,
plus, sorry,
this
gamma
has to
c
be,
means
Yeah, that has
we
to
have
be between 0 and 1.
between 0 and 1. For gamma c between 0 and 1, this will be bounded. And this is not a difficult choice because for every c, we can choose a gamma. For all c, we can choose a gamma. Okay, so it is less than infinity. It's not equal, it is less than equal because there we are taking more terms. Okay, so now we showed that it is bounded for gamma c between 0 and 1. Okay, so now the last part of the question is we have to find out the martingale sequence and we have to write down the emphatic TD0 update equation. So let us do that, very easy. So let's write down the first step for writing martingale sequences. Mn plus alpha n delta n phi of Sn. Okay, phi of Sn an rho n delta n phi of Sn. So first step, tell me what would be the first step? So let us write this as f emphatic of Wn Sn. What will I define this as? Can you tell me?
Summation of
The expected value of, again, which is the policy we are using? Which is the
we,
policy?
behavior.
we are using beta, yeah, behavior policy, and the expectation is of kn, rho n, delta n, phi of Sn.
Delta n phi of Sn given the same history, right?
Yeah.
Now you tell me
Now
Kn
I
is
think kn is bounded, and we can use that bound and then probably say that it's less than equal to the bound into e beta
no,
of rho
see,
n.
we can equal, you can find it equally. No need to even bound it. See, rho n plus Kn minus 1, yes or no? Do you agree? Fine. Kn
Yes,
is, so rho n is minus 1 is what? Mu of or pi of
Phi of
Sn n minus 1 given Sn minus 1, yes or no? By An minus 1 by Sn minus 1, yes or no?
yeah.
See, An minus 1, Sn minus 1 belongs to the history, yes or no? We have defined everything till Sn to be in the history. Clear? This has everything, right? A0, W0, A0, S0, W1, S1, A1, W2 dot 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 up to Sn. It has everything, yes or no?
yes,
So what can I do with Kn? Kn is fixed, yes or no? It's constant because Sn minus 1 is known.
yes, we know the history.
Correct. So I can write this as Kn. See, now again I have got down my, this is the trick that Sutton is using. Because I already know the history and I know that these algorithm converges by SD theorems. Therefore, I can clearly put out the Kn outside. And as soon as I do that, I can write this as Equation 1. Yes or no? Which is the same as?
K of
Correct?
M. Yes.
So now my new equation becomes Wn plus 1 is equal to Wn plus alpha n K of n f of Wn Sn minus or plus Mn plus 1, where Mn plus 1 is equal to, or Mn plus 1 of the emphatic is equal to what? Kn phi n. Do you agree? Okay, no questions. All I'm trying to do is going to the same form where I can use the stationary, the limiting ODE. But now I am not done yet. Do you see this Kn is stochastic? Yes or no? The Kn is stochastic because it depends on the policies. What can I do now?
Yes,
Is the
for
question.
different trajectories, I'll get different K.
Correct. So I can do something like this. I saw that this is bounded, which means
Yeah,
these
so we
Kns
have
should
to,
converge.
yeah.
I can do some. Can I do something like this? As at infinity, I want the Kns to converge so that Wt goes to W star. So I will do something like this. Kn given Sn is equal to S is some Ks, okay, which is fixed. This is a constant, correct? Which only depends on the state. This is fine because we saw that it is going to converge. It's bounded, correct? So I can put an infinite bound on it that it will not go above this. Is it clear? This is not a difficult thing to anyways prove. We can always prove it, but it is not even, we don't even need to prove it because this is anyways bounded. So once I do that, can I write Kn? So we have been doing this all the while. How can I write this in terms of constants and in terms of stochastic terms, noise terms? Can you tell me? Very simple. I will have to add and subtract. Plus K of S, Kn minus K of S, f of omega n Sn. Right? Yes or no? This is the same. Yes or no? Questions? See, as n tends to
No, same
infinity,
thing.
yes, limit n tends to infinity. Look at this term in expectation. This also goes to Kn. This term will go to 0, vanishing error. Vanishing error. This will go to K of S, f of omega n Sn. Because this term, the second term, will not depend on Kn at all. So I can write down the emphatic algorithm in Wn plus 1 as Wn plus alpha n Ks f of omega, or Sn I'll put here because it's the nth term, comma Sn plus K of n minus K of S f of omega n Sn plus the martingale n plus 1 emphatic. So this entire term is now a new martingale. Right? So this, even if you do not represent this as a martingale, this is a martingale, and this is also vanishing to zero. To zero. This is a new martingale m tilde n plus 1 as kn minus ks omega s n as n tends to infinity. Emphatic. So this is, again, the update can be written as alpha n ks n Sn plus mn plus 1 tilde emphatic. Okay, so now I have got this entire equation. Now tell me what will be the W star or W, the ODE for emphatic TD0. What will it be?
The
Summation
OD
of
will be, yeah, summation of d beta into
K S f of omega t s. Yes or no? I think I made some writing errors on the top. Wait just a moment. Where did I write the? Sorry, very sorry. This should be WT. And this is summed over all S. Yeah, you didn't tell me because this is a OD in T. So this omega has to be OD in T. Okay, this is fine. This is also fine. So now we say that this term is referred to as the D emphatic of S. S in S, D emphatic of S, f of WT, comma S. Note, DE of S is not a distribution anymore. Distribution, because summation of DE of S is not guaranteed to be 1, not guaranteed. Clearly, because it's a product of two terms which are not anyways related to make them 1. But this equation will still hold. The solution will be W star will be pi transpose D emphatic. D is diagonal of DE of S, I minus gamma P mu P pi inverse phi transpose D emphatic R. Is this fine? Whatever we changed, so only the D's change. Only these change. And it can be shown, stop here, shown that phi transpose DE 1 minus gamma P pi is invertible. So this is your emphatic convergence point. So when you are doing off policy algorithms, to get a fixed point of convergence, we may have to do this emphatic update term. So any questions? If there are none, so we can go to the questions regarding the assignments.
Would you discuss the last part of the derivation once? I just lost you.
Okay. So which part of the derivation do you want me to discuss? So did you find the
This
KS
is
is
okay.
fine?
This is fine. It is.
This I just
The
added
OD.
and subtracted KS.
Yeah,
The
that
OD,
is fine. The OT,
Okay.
you construction of the OT. That's all. How you made d beta d. I
Correct.
mean,
So
how you made d beta ks as de.
I just wrote that's the definition. I'm defining
Okay.
d of s as d beta of s into k of s. Just for simplicity. Define. This is definition.
Sorry, I just
No,
lost
no,
you.
no. The d is that's why I said no. D is not a distribution. It's a definition. So it's to decrease notation. That's why I did that. This is the point
Yeah,
where you will
I would.
converge. Yeah, and it can be shown it is invertible. You can look at the paper if you're interested. Yeah, so I'll stop sharing from my tab if there's no more questions, which I think it was very understandable if you followed till today. I'll just yeah. Now I can share my screen from here. Yeah. So the assignment 1, the first part is a theory, and then
Assignment 1 is essentially, oh,
this one, right? This is the same question that I gave in class. I did solve in class. Now you want me to tell how to help you regarding the TD lambda algorithm, or have you been able to apply? Or do you have any questions regarding this?
No, yeah, we have some shortcomings in our conceptions, but we'll clarify it on our own. Like, I'd rather that we work and clarify those things on our own. Like,
So you said that there was some problem regarding the coding. I
no,
heard.
TD, when we actually told you about our doubts about TD lambda, you said that you're gonna uh, assign us the TD lambda in the second assignment. Here, in the first assignment, we have no problems. Only the thing with the code I told you the last day that it would have been plus the for the this arm for the second arm uniform of -1 to 2. You had defined the expected value as b minus a by 2, which it would have been b plus a by 2. That's the only thing.
I see. You are saying that you are talking about the second. This is the first assignment. We don't have any TD
Yeah,
lambda yet. We had
yeah.
value iteration. Yeah. UCB.
There were no
You were able to implement the UCB algorithm.
UCB
yeah,
you had implemented only. UCB you had implemented. You had only said that use
we had
to
to gradient.
gradient descent and compare.
Yeah. I don't know.
Yeah,
UCB is like gradient using the gradient descent only, upper confidence bound. Yeah, I had implemented using
yeah, normally.
normal yeah, the what is it called? The dynamic programming approach.
And what we did was we used the formula of updating the activation functions using
Correct.
yeah
Yeah. The
r minus
gradient
r
descent update.
yeah r minus r mean one indicator minus that.
Good. Okay. Great. So okay, then I'll stop today. We'll see you next week. We're almost there. Yeah, tell me.
And
I'll
like
stop
yeah, fine.
I'll stop recording if you don't have any questions regarding the course. Okay, I'll stop recording then.